Hello, this is Dr. Keith Schubert, and this is going to be our video lecture on how to do floating point addition. So if we consider floating point addition for a second, if we've got a 4-digit decimal number, so we'll start with a decimal example, and we've got 9.999 times 10 to the first, 1.61 times 10 to the minus 1. If you remember when we did multiply, everything was multiplied so we could commute. Now it's addition. You can't really commute. So what we need to do is use the distributive property, which means we want to have whatever is this number here be the same as this one, and then we can just pull that out, and then we can just add these terms normally. In order for that to happen, I got to make this 10 to the first. We usually go to the larger of the two. Now, in order to get this to 10 to the first, I have to now shift this one 2 up, which means this has to be shifted 2 down to be consistent. So that's what they've done with it. They've kept this one 10 to the 1. They've made this 10 to the 1. In order to do it, it took, remember the radix point was here, 1, 2 shifts. Now at that point, we can take a look. The significans can be added because now distributive property, you pull it out, it's just that plus that. Now note when that happens, this one's going to be shifted over, so it is quite possible that you can end up with this one being so far it makes almost no change on here. So what we do is we normally carry 3 bits past it. Right? We have what's called this next digit after is called the guard, and then we have the round bit, and then we have another bit we call the sticky bit. And the sticky bit will be set to be everything in this one after the guard and the round added up together. So it ends up being an OR of all the remaining bits. And it is OR instead of XOR, so the more of them you have, the more you get into the sticky bit. Alright, so that's the basic idea, and that allows us, those 3 extra bits, allows us to do more accurate addition to handle the fact that, rounding needs to be done. So now that they're set up, in this case, we're just going to add them because we do have the correct number of digits. Just add them together, 9 and 9 plus this. So it just all carries up nicely. The 6 from here is put 1 out. That makes it 10 plus 0.015. Boom. Those are the same, so they carry in. And then we just normalize because this is now 10, so we have to shift that over. And so we shifted it over, but that means we made this one smaller. That one's got to get larger. We round and renormalize as necessary because remember we had those extra bits, but in this case there was no need for it. So let's take a look at the same thing in binary. Now we've got a 4-digit binary, right? So 1.000 times 2 to the minus 1. This is that half. This time we're going to add our minus 0.4375. These are the same numbers as last time, so should be no problem. Now in order to do this, this one is a less number, so we have to increase this by 1, which means we're going to have to shift the radix point. That's what you see here. Radix point shifted, and then that increase, so now it's the same. Distributive you pull out, so you can just add this and this. Alright, so when you add the significans together, you're going to end up with that minus, this one, and so that's where we get the number here, right? 1.000 minus 0.111. Alright, so this is 1 minus, and that's 7/8, so you get 1/8. That's all 2 to the minus 1. Again, here, that don't get confused by this. This should be an exponent. It just didn't get tagged right on the slide, evidently. So now we renormalize the result and check for under overflow. So in this case, we have to renormalize, so we're going to have to move over. Now remember, in this case, since we're doing them, it looks like we got not much left here, but we would actually have the guard round and sticky in real life. And so it shifts in. Now in this case, there's still no error because it all fit nicely. But when we move this one over, this one commensurately has to be decreased. So you 1, 2, 3 over, which means we're going to have to, this got bigger by 3, this one has to get smaller by 3. And then take care of any round and renormalize as it goes on. We're fine. And so we notice we get the correct answer. let me just give a little commentary about the hardware here. I'm not going to do a lot more addition examples. Um, it's a lot more complicated than integer adders are. Um, just as a note though, it's really not that much worse than multiplication. It is a little bit worse. We'll talk about the hardware for it in a sec in more detail, but um, it is more complicated than integer addition. Doing it in one clock cycle means that clock would have to be really slow. So we have to do multiple clock cycles in order to take this. Since it's several clock cycles, we can pipeline it, which we'll talk about in class in a few days here. But to handle pipelining, it has to be multiple cycles for this to go. So we usually make a separate little unit, calculates to the side, and can return back its answer so other things can keep moving on. As I mentioned, it's similar complexity to the adder in terms of true complexity. It's a little more work for human beings because you have to do that normalization step to make the smaller the size of the bigger. I'm not going to make you do a lot of problems on these just because I think they get a little tedious. Multiplication carries the thought through well and is a little more natural to humans. The only difference is multiplication obviously multiplies the significans, and the adder adds them after they've been normalized. Floating point arithmetic hardware usually handles all this, so we want to handle one, and we've got a conversion of them. So like I said, they normally are normalized. So let's take a look at it, what this goes on. They haven't shown how the sign goes. What normally happens is we take a look at those two sign bits and we do an exclusive OR, and that exclusive OR determines whether this adder down here is going to add or subtract. So we would just exclusive OR these two bits and then put that into the carry in, and then we could take each of these ones here and do our exclusive ORs for each bit, and take the sign from it and carry it down so that it handle our negation of it. So we would take the sign of that and then AND it with the exclusive OR, because we only want to flip the bits if we're actually going to do subtraction. So the exclusive OR tells us subtraction, and then ANDing that with the sign bit tells us should we flip. Right? So again, exclusive OR ANDed with this will tell me should I flip these. So that will get me my flips. They didn't draw that in, and I'm presuming because that's just a little bit uglier. Then what we need to do is we have to take the two exponents and find out which one's bigger. So a little small AOU, we just take the difference between the two, and that comes down into the control unit. And if this one minus that one is positive, this one was bigger. So it'll tell you pick this one. If this one minus that one is negative, it'll tell you pick that one. And if it's equal to 0, then it doesn't matter. So it usually picks 0 as the default. The other thing that it'll do is when you come in here, the fractional part with a 1 added in, truthfully, will have, it has to pick which one. This is the one that'll get shifted, so it'll tell it how much the difference was to the shifter. And it'll pick the one that's smaller to go into the shifter so it can choose between the two. And it knows which one's smaller because of this. And it does the opposite. So whatever's here, the negation of that value is here. So the smaller goes here, the larger goes here. And then it'll do add or subtract based on what the sign differences was. Right? Obviously, the one's complement we calculated there, and then the potential plus 1. So we can now have a true add or subtractor for it. And then the result of this not only comes in to be handled, but it also comes out to be analyzed. Doesn't need to have the shift. And so it can shift right or left, whatever the value is, and then the rounding hardware comes in, and it might need to be fed back in. So that was that reason for this backer line here, is it comes up to the control unit and determines, do I need to continue fixing it for the guard and round and so on bits. And then it takes a look at the exponents coming in, and it handles, if it did have to do any shifts, it modifies it and puts the values in. And then the sign bit is calculate from what was the sign here if it was 2's complement. So it's either going to be the sign bits here if they're the same carried down. If they're not the same, it'll take a look at what the sign bit after subtraction was. That's basically the hardware with a couple modifications they didn't put in for you. So we just note again, it's similar complexity. It's actually a little bit smaller for the multiplier, and it takes care of all that stuff for us. So we've now got a basic idea of how to do addition. We've seen how to build it into hardware. So at this point, you've got all you need.